Last time we looked at double integrals for the volume of a sphere. We reminded ourselves of what these integrals look like. And then we practiced chopping up parts of the sphere by controlling the values of x and y, or the values of r and theta that we plugged into the integral. So we have a lot of control over where we integrate based on the endpoints of the interval. That's the big challenge here. Notice that in all this work, we haven't actually done any calculus calculations. We've been using calculus notation to describe regions. And now we want to continue doing that practice using calculus notation to describe solids. So we're going to write some triple integrals for the volume of a sphere. Remember that what we're going to do here is we're going to write the integral over W, a solid W, of 1 dV. So this will give us the volume of the solid W. 1 is a unitless placeholder function. There's no units on the 1. All the units are going to come from dV. And so this will give us the volume of the solid W. So we'll note that 1 does not have any units. The 1 does not have units. Our units comes from our dV. dV is going to be a little chunk of volume. So here is where we're going to get our volume units. Right now we have the mechanics in play to deal with two kinds of 3D coordinates. Excuse me. One style of coordinates is going to be rectangular coordinates. This will just be dy dx and a dy. So rectangular coordinates in R3 are just like rectangular coordinates in R2 with a z-axis. We just stick a z-axis onto our rectangular coordinates. We just take our rectangular coordinates and add a z-axis. We're just taking our regular XY coordinates, our rectangular coordinates in R2, sticking a z-axis through the origin, and now we have rectangular coordinates in R3. dx, dy, and dz are all going to be length, or all going to represent distance. So dv will be the cube of distance, which is volume. The other type of coordinate that is easy to adapt are polar coordinates. Polar coordinates, when we upgrade to R3, we do the same thing. We just take polar coordinates, we put a z-axis through the pole, and now we have cylindrical coordinates. So we call that cylindrical coordinates. Remember that theta does not represent a distance, so I multiply r times d theta to get a distance. But r is a distance. And all we're going to add now is a dz. And here we have cylindrical coordinates. We just take polar coordinates and add a z-axis. So we get rectangular coordinates plus a z-axis. That's just still rectangular coordinates, an extension of what we're doing. For cylindrical coordinates, we take polar coordinates to describe the floor, and we stick a z-axis in the pole, and then those are cylindrical coordinates. I think I went around in a circle now, which is appropriate because it's cylindrical coordinates. When writing a triple integral in rectangular and cylindrical coordinates, just like writing a triple integral actually in any coordinates, we just look at our three coordinates, so x, y, and z, and we say what's x between, what's y between, what's z between. And for cylindrical coordinates, we'll say what's r between, what's theta between, and what's z between. So our triple integral, the what's x between and what's y between, that's the same. So in rectangular coordinates, x will go from negative r to r. Y still goes from the negative square roots to the positive square roots. Since we've already done the double integral, the thinking is the same. This 2 square root of r squared minus x squared minus y squared came from taking the top square root, the positive square root, and subtracting the negative square root. That's why we had 2 of them. So the bottom of this, the z, is the negative square roots. The top is the positive square roots. This is how we came up with this expression in the first place. We solve for z, the z hemispheres. I took the bottom half, negative square roots, to the top half, positive square roots. So we've set up a triple integral just by saying what's x between, what's y between, and what's z between. So this is just the integral of 1. And then the order, it looks like I did a dz integral first. Then I did my dy integral. And then we did the dx integral. We want to note that the first step in evaluating this triple integral will lead us to the double integral that we had before. That's why I picked this order, because it would just lead directly to the double integral that we had before. Won't have to change my variables, nothing in my sleeves, presto. So the first thing we would integrate is 1 dz. Our first integral is 1 dz. So the first integral that we calculate, the dz integral, will just send us directly to the double integral that we had before. The integral of 1 dz is z And then we would evaluate from the negative square roots to the positive square roots. That means we'll take the positive square roots minus the negative square roots and end up with 2 of the square roots. The integral of 1 dz is going to be a z. We plug in the endpoints and subtract. That's where we get the 2 square roots of r squared minus x squared minus y squared. We get our double integral from before. I didn't write a lot of the details in the middle here. Here we are integrating. Here we are plugging in the endpoints, and here's what we ended up with, the double integral that we already knew about. One thing we want to note is that in this rectangular coordinates, oh wait, no, sorry. There's the y squared right there. I was looking at this x squared. And I thought, oh, that's easy to integrate with respect to y, but oh no, trig substitution. Bad face. So that kind of that first step, we get away with no trig substitution because it's going up and down on the z. But now we're into the round stuff. Now stuff is round, so we have to go. Our x and y are related in a circle. That's round stuff. Rectangular coordinates are very bad at round things. That's why we have polar coordinates. Polar coordinates are going to be very bad at rectangular things. Say the interval from x goes from 0 to 5 and y goes from 0 to 3. That would be kind of a pain in the butt to describe in polar coordinates. But when things are rectangular, we'll use rectangular coordinates. When things are polar, we'll use polar coordinates. Better to have both than to just have one all the time. Any questions? So since cylindrical coordinates are just polar coordinates plus a z-axis, we do almost the same thing for our cylindrical coordinate triple integral. The z part is still going to be the same because we're using the same z-axis for cylindrical and rectangular coordinates. We've replaced the x and y axes with just a pole. We remember where the positive x-axis is because that's the place from which we measure our thetas. But in cylindrical coordinates, if I describe what r is between, r still goes from 0 to capital R. If I want the whole sphere, then theta still goes from 0 to 2 pi. What's z between is the same as what z was between in rectangular coordinates because it's the same z-axis. Z goes from the negative square roots. But I don't want to use x and y. I have to replace my x squared plus y squared with r squared. So I have to write things in cylindrical in polar coordinates. Well, cylindrical coordinates. But we're still going from the negative square roots up to the positive square roots. We're still integrating the function 1. The first variable we're integrating is dz. The next variable we're integrating is d theta, but d theta is not a distance, so I have to multiply by r with arc length formula. And then the last variable we'll integrate is dr. I remember. Oh, I did remember. This will give us a much nicer integration all the way through because a sphere is just 3 intervals. Oh, it's 3 intervals in spherical coordinates. The round stuff is just 2 intervals. Instead of having to describe the y's with 2 different functions, to get a circle, I just say theta from 0 to 2 pi, r from 0 to capital R. Once again, our first integral, the dz, will just send us to the double integral in polar coordinates. The integral of 1r dz. So the r, it shows up to make the d theta into a distance, but it's part of the function we're integrating. So it's an extra factor of r. We're going to be integrating it, but the first integral is z. So the integral of r with respect to z is rz. Then we evaluate this from the negative square root to the positive square roots. We're plugging that in for the z, so I get r times the positive square roots minus r times the negative square roots. Negative and negative makes a positive, so I get 2r times the square root. R should have stayed green this whole time, but this part is not good. That's the double integral that we had before. what we notice in our rectangular coordinates, because our rectangular coordinates are so bad at describing circles, we had to do trigonometric substitution. But notice that when we have polar coordinates, since polar coordinates are really good at describing circles, and we're just integrating over two intervals, now our integration is super simple. Where before we had trigonometric substitution, here we have a plain vanilla substitution. W is equal to r squared minus r squared. dw is negative 2r dr. Oh, we're not even ready to do that. We have to do theta first, but anyway. I'm a whole integral ahead. But it doesn't matter what order I do these integrals in. I could switch the order if I want, because r to r and 0 to 2 pi, this circle is just two intervals. Because we're in polar coordinates, and polar coordinates are really good at describing round things. Round things are just going to be couples of integrals. Sorry, intervals. Rectangular coordinates, this is a mess, and I have to muck with my functions. But in polar coordinates, round stuff, no problem. Any questions? It's one of the things that trigonometric substitution is trying to do. It's trying to resolve this round stuff versus rectangular stuff. How's everybody okay? So next time you're doing trigonometric substitution, see, this is the kind of one of the bummer things about Calc 3. For the most part, we're not going to be doing a lot of trig substitution. I can use it to threaten you. Like in the previous examples, like, oh, look, we'll have to do trigonometric substitution here. Ooh. But we don't get to go back to trigonometric substitution and see the conversion to polar coordinates and the conversion back. There's a little bit of what we're just switching to polar coordinates. Because in math, we only have three great tricks, or we have lots of tricks, but we have the three great tricks of math. Add 0, multiply by 1, change coordinates. Those are the main things that we do. We look at this integral here and say, ah, gross. I'm going to change from these rectangular coordinates, and I'm going to say y is r squared minus x squared times, what is this going to be? Sine of theta. I'm going to switch to those round coordinates. I'm going to bring theta into this. Here, that wasn't a problem. Everything's already round. This is where things have already been rounded out. Any questions? How's everybody okay? Right now, you're not sure. I'm like, oh, is everybody okay? I don't know. Is there some trigonometric substitution in our future? I don't know. I'm not allowed to look into your future. But then you're like, oh, well, if it's future past Calc 3, then I'm not worried about the trig substitution that'll show up. That's far enough in the future. I care more right now about the immediate future. Are you going to make us do some trigonometric substitution? And I'm like, oh, no. And then so now you're like, oh, then we're all right. You know what I mean? I don't know if I've done it this class. I don't do it as much in Calc 3. I just kind of assume. Actually, I usually say I just kind of assume that you all know how to do algebra, but in the back of my mind, I know that you don't. I know that you do, but not really. I think I've asked this one before. Can anybody here explain to me counting? Not just like how to count. Don't give me an example of how we normally count. Explain the process to me. How does counting work? How would you explain counting to an adult alien? Not how we explain it to children, because at this point, that's your understanding of counting. It's the same as when you first started to learn how to count when you were, how old are you when you learned to count? I'm gonna have to call up, we have a ECE department, we have a childhood development department. There are experts on campus. I need to call them up, say, oh, dude, when do children learn to count? As much experience as I have is teaching math to people, I have no idea. My main focus has been on teaching calculus to be when it's new, and fixing the things that my predecessors have broken. Right? Because you were like taught arithmetic, and they're like, I'll do PEMDAS. And I'm like, oh, son of a bitch, everybody's got freaking PEMDAS. Now I try to fix that. Try to fix that PEMDAS crap. I'm like, oh, here, let's solve this quadratic equation. So I use a quadratic formula. Son of a bitch. All these students have friggin' quadratic formula. I'm like, oh, how about completing the square? We were told to not complete the square and just use a quadratic formula. Did you know that every time you use a quadratic formula, you are completing the square? You're just taking a shortcut because you're lazy. I'm just kidding. Lazy isn't an insult. Every single human is lazy about something somewhere. Everybody has something that they are lazy about. Right now, we think of lazy as a bad word. It's like, oh, no, I'm not lazy about anything. It's like, oh, really? Is your laundry done? Are there dishes in your sink? Yeah, you're lazy about something. Have you added due dates to your current crop of assignments? That might be only specific to one person in the lab. Anyway, what are we talking about? Oh, yes. So we got our polar coordinates. They're very good at describing round stuff. And notice that when we use polar coordinates on the round stuff, our integration even gets easier. Use the right coordinates. Use the right tool for the job. This is why we need all these different tools for things. But just like Skywalkers, there is another. And when we run out, we'll just make some more. And then they're like, oh, what if it doesn't make sense? We'll do it anyway because the audience will like it. What I'm doing is accusing Disney of just leaning into fan service. That's all they're doing. The fans would really like that one. Let's do it. It doesn't make sense. All the writers are like, well, no, that doesn't really make sense. It's like, I'll do the fan service now. It's like, okay, Disney. Spherical coordinates. These ones are actually different. This is not just like sticking a z-axis onto some coordinates that we had before. So we got to talk about spherical coordinates. Spherical coordinates is going to be one distance and two angles. Oh, I can't color coordinate. This is the next step in the progression. Rectangular coordinates, three distances. Polar coordinates, replace one of the distances with an angle. Two distances, one angle. Spherical coordinates, replace another one of the distances with an angle. One distance, two angles. We can't go any further than that. We need something about distance. We can't just use three angles, because then there's no concept of how far away anything is. So that one's right out. As usual, we're going to use our regular rectangular coordinates. And we're going to try to describe a point in space with one distance and two angles. I always miss. Can't really do it without the line down on the bottom. So here are the rectangular coordinates for that point in space. The polar coordinates, I would care about the distance here that would be the length r. And I would care about the angle. Try to view this swinging door from the XZ plane, kind of swinging around towards the y-axis. The angle from the positive x-axis to where we drew r, that's going to be theta. The z is the same in both polar and rectangular coordinates. So this point x, y, z in rectangular coordinates will be the points R, theta, and Z in cylindrical coordinates. X and Y is one way to describe R2. R and theta is another way to describe R2. Rectangular and cylindrical coordinates just turn R2 into R3 by sticking a Z-axis on there. So now what we have to do is describe this with spherical coordinates. I only get one distance, so I have no choice where to put the distance. I usually say we have one choice, but then that line always bugged me in Lord of the Rings. You have but one choice. I go, then you don't have a choice. I mean, I know what he meant. There's only one choice that makes sense, because they could have chose to just like, oh, we're just going to go home. And they're like, oh, then, you know, sour. What about, you know, Mordor, the orcs and stuff? Forget about it. I mean, it sounds ridiculous when you say it like that, but like climate change. But anyway, we have but one choice of where we can put our distance. And that's from the origin to the point. How far is the point away from the origin? I don't know what color I want rho to be. I was using, my first one has always been like orange, but rho is going to be the distance from the origin to the points. That's the one distance we get. It's where we have to put the distance. So our first coordinate is going to be the distance from the origin to the points. And for that, we're going to use a lowercase rho. Our second coordinate is going to be the same theta that we use in cylindrical coordinates. Our theta, our middle coordinate, is going to be the same theta that we use in cylindrical and polar coordinates. It's going to be measured from the positive x-axis to the side, to the point directly underneath the point that we're looking at on the xy plane, or on the r theta plane, I should say, since we're using theta. We need a third, we need a third coordinate, which is going to be another angle. Theta is measured from the positive x-axis. I need something involving the up and down. So our third coordinate will be phi, the angle measured from the positive z-axis. So sometimes I will say phi. So this is the angle measured from the positive z-axis. So I got one distance and two angles. This is going to be our opening picture tomorrow. We're going to remind ourselves where we measure things. I'm telling myself right now that I will draw this beforehand, but you know very well that I'm not. Because as we say, as we mentioned before, as we have observed, everybody is lazy about something. Any questions? Comments? Snide remarks? All right, that's going to do it for today. I will see y'all on tomorrow. But have a good day and thanks for playing.